Morning, my name is DC Eagle from NASA's Jet Propulsion Lab in Pasadena, California. We're here today to talk about the Juno mission to Jupiter. And currently, Juno is 7,071,000 miles from the gas giant, and on July 4th, it's going to light up its main engine and head into orbit. So to talk about Juno today and its science and Jupiter orbit insertion, we have with us Ed Hurst, Juno mission manager from the Jet Propulsion Laboratory. Scott Bolton, Juno Principal Investigator from the Southwest Research Institute in San Antonio. Steve Levin, Juno Project Scientist from JPL. Jack Connerny, he's the Juno Deputy Principal Investigator and Magnetometer Investigation Lead from the NASA Goddard Space Flight Center in Greenbelt, Maryland. Fran Bagenal, Juno Magnetospheres Co-Investigator from the University of Colorado at Boulder. So before we start things off with our panel today, I'd like to introduce Diane Brown. She's the Juno Program Executive from NASA Washington. Thank you.
Good morning. We could not be more excited about being back on Jupiter's doorstep and being so close to our arrival on Monday. NASA has been to Jupiter before, but never this close. And we know a lot about Jupiter from previous missions, but Juno is poised to answer the questions that we still have. Juno is the second of 3 missions within NASA's New Frontiers program, which is in the Science Mission Directorate in the Planetary Science Division. The New Horizons mission, which some of you will probably remember last July, gave us those amazing photos as it flew past Pluto. And the OSIRIS-REx mission is scheduled to launch this September, and it will fly out to the near-Earth asteroid Bennu and do a sample return, and we expect to see those samples as early as 2023. Juno was selected in the second announcement of opportunities for the New Frontiers program. It was selected in 2005, and it launched in 2011. The Marshall Space Flight Center in Huntsville, Alabama manages the New Frontiers program for the Planetary Science Division. NASA has a long history of milestones on the 4th of July, and we look forward to making our own fireworks this year. We could not have reached this milestone without the years of dedicated work and planning by the entire Juno science team and the mission team, and we thank them all for their dedication. NASA's vision is to reach for new heights and reveal the unknown for the benefit of humankind, and Juno is a perfect example of how NASA reaches for that vision. Thank you.
Okay, thank you, Diane. And to start things off with our panel, we'll go back to Ed Hurst, the mission manager for Juno.
Thank you, DC. I wanted to start out reminding people of some salient features on our spacecraft. The most prominent thing that you see are our large solar panels. Each of them are 10 meters wide, 10 meters long, and tip to tip they span rim to rim on a basketball court. They produce 500 watts at Jupiter range, and that's enough power to produce, to power our instruments and all the electronics inside. The other salient feature is right under the high gain antenna. It's this box that's under here. That's what we call our electronics vault. Inside of that box, we have all of our sensitive electronics. And that's what that vault is made out of titanium, and it's going to protect the electronics from the intense radiation belts while we're at Jupiter. The star of the show on July 4th is on the back side, and you see here we have a main engine cover, and right where the stand comes into the back is our main engine nozzle, and that is the engine that's going to produce about 645 newtons of force and over 35 minutes slow the spacecraft down so that we get into orbit. So what have we been doing for the last few days to get ready for July 4th? 10 days ago, we opened that main engine cover so that the engine would be ready to fire when we get to July 4th. And a couple of days ago, we pressurized the whole system so that the engine is ready to go, all the propulsion and all of the pipes and valves are all ready to fire. Today, we're sending the last commands up to the spacecraft, and once those commands are sent, it'll be hands-off from the team here on the ground. We'll continue to monitor the spacecraft and make sure that everything is executing as we expect it to execute. But the spacecraft is on its own, and it's designed to take care of itself along with all of the command sequences that we've sent it. So to show you a little bit more about what's going to happen on July 4th, can I have the first animation, or my only animation? What you see on the screen, the little puffs that you see right now are our smaller thrusters. They're 4.5 newtons in size, and they're reorienting the spacecraft so that we get the engine in the proper direction so that when it fires, we're slowing the spacecraft down. You now see the thrusters, they're spinning the spacecraft up from 2 revolutions per minute to 5 revolutions per minute, so that when we do the burn that you're seeing on the screen now, the spacecraft is in a stable configuration, and over that 35 minutes, we get the thrust in the direction that we need to get it. We then slow the spacecraft back down in revolutions to 2 RPM, and we turn the vehicle back to the sun to start recharging the batteries and start communicating back with Earth. While we're doing the burn, we are in communication with the spacecraft via tones. It's a modulation that we get on the radio signal that tells us that all the events are happening as designed. So that's what we're looking forward to on July 4th, and I'll hand it over to Scott to start talking about some of the science.
Thanks, Ed. So I'm just so excited to be here. I can't express that enough. I mean, in just a few days, we're about to arrive at Jupiter. And it's hard to believe. I'm so proud to be part of this team that has accomplished all of this. You know, what Juno is really about is learning about the recipe for how solar systems are made. Scientists don't really understand how the planets are made. We know after the sun formed, something happened and we were able to form Jupiter. It took up more than half of the material that was left over. And it's a little bit different than the sun, and we don't completely understand that, and that's really the first step in that recipe is how do you make solar systems? Something happens that allows the star to be born, and then afterwards the planets. And that first step eventually leads to us. And Juno's poised to be able to make some great progress on learning about that step, not only to explain how our solar system formed and maybe how we got here, but how other solar systems that NASA's discovering in other star systems, how they get created. Jupiter's our example. And in order to accomplish the science objectives that we're set out to do and the measurements that we want, we have a set of tools on board Juno. We call them science instruments, but they're just different tools that we use, tricks of the trade, so to speak. And I want to give you a little idea how those work. They're situated around the spacecraft that you're a little bit familiar with from these images and what Ed just explained. And I'll show you that on this first animation. You'll see sort of an X-ray view. The things that are in color are the science instruments. They're all looking out between the solar arrays. The solar arrays are, of course, the spacecraft's spinning, so everybody gets their turn to look at Jupiter. This was a very efficient design. In the middle, you see all these boxes cluttered together. That's inside of our radiation vault. So that's a giant box that is about 400 pounds of titanium to shield sort of the vital organs of Juno. I mean, this is where the computer and the brains lie, all the sensitive electronics. We have to shield it because Jupiter is basically the harshest region in the entire solar system. It is a planet on steroids. Everything about it is extreme. The radiation would just not only kill people, but it would knock out our electronics, and so everything's protected inside. That was one of the aspects of our design that was very efficient. We decided, this is the first time NASA's tried that. We put all the electronics in this vault. Another aspect was having this spin where the instruments are able to look out between the solar arrays. So we don't have to spend a lot of efforts turning the spacecraft. Everybody kind of gets their turn as we spin through. So it was a very simple, efficient design. And that's sort of a theme throughout Juno. What I'm going to show you now is some exciting new data that we just got last week. But before I show that to you, let me give you a little bit of a background of what you're going to see. So as you travel from the Earth to Jupiter, you're traveling through interplanetary space. You're basically in the sun's domain. The sun fills interplanetary space with charged particles. We call them the solar wind. It's blowing through space. That solar wind, these charged particles, ions and electrons and protons, they basically would bang into Earth, but the Earth has a protective shield called a magnetosphere, a magnetic field around it. That's like a cavity or a balloon that's inside this other cavity. The first cavity is the sun's domain, and then inside that balloon, if you can think of it, another balloon exists, which is the Earth's balloon, and it's protected. And inside that, behind that shield, is the Earth's domain, our charged particles. Well, Jupiter has its own magnetosphere, and in fact, it's like everything else with Jupiter, it's the biggest. It's the biggest object in the entire solar system, is Jupiter's magnetosphere. If you could see it, it would look like the size of the moon. But of course, it's an invisible force field. But inside that magnetosphere is Jupiter's domain. That's filled with its particles. It's blocked out the sun's particles. So when you get close enough to Jupiter, you move a transition from being in interplanetary space, the sun's domain, to going into Jupiter's domain. That means you're getting pretty close. Well, we crossed that boundary about a week ago, last Friday or so. And the science team spent some time arguing which day it was, because it wasn't completely clear. But we came to a conclusion that we think it happened last week, and I have that data to show to you. What you're going to see is something we call a spectrogram, which is a little bit complicated. It shows frequency and time, and the colors represent intensity of the waves. It's from our waves instrument, so it's looking at plasma wave data. But the unique thing about that data is that data can be converted into audio. In other words, it's coming into a radio frequency, but we can hear some of those radio frequencies, just like you hear music. So the human ear can hear about 20 to 20,000 hertz, like we're measuring electromagnetic waves that are in that range, so we can convert those into audio, and we can actually listen to what it's like to leave the sun and enter Jupiter. And that's what you're going to hear. Can I have that animation? Just the sound of it can tell you it's non-trivial to go into Jupiter. And so what you just crossed was what scientists call a bow shock. It's the same kind of thing that you hear about if you're on listening about how a supersonic jet works, right? It flies through the fluid or the air and makes a shock in front, a shock wave. A boat going through the ocean creates a bow, right? Shock, a wave in front of that. That's what Jupiter's doing. It's plowing through the sun's domain, and it's created this bow shock, and we just crossed it. So we're there. We still got a lot to do on July 4th, and I'm still nervous. But we crossed it. We're in Jupiter's domain at this point, and we're measuring the particles that are Jupiter, not the sun. So that was a big deal. So Juno does other kinds of science. I mean, besides the recipe and this magnetosphere crossing, we're going to look at the whole polar magnetosphere, and you're going to hear that in a little bit. But a lot of what Juno is about is looking inside of Jupiter, seeing what is in the interior. And we basically have scientific instruments that look inside the planet in every way we know how. And that's what you're going to hear in the next couple of talks, is different ways to look inside of Jupiter, beneath those beautiful clouds and meteorological features like the Great Red Spot and the zones and belts. And then eventually how we explore the polar magnetosphere. Okay, and so for that first part, I'm going to turn to Steve Levin, a good friend of ours.
Hi. So I'm going to tell you a little bit about the microwave radiometer instrument and how we measure what's probably the single most important number that Juno is going to bring back from Jupiter. And that's how much water does Jupiter have. The amount of water inside Jupiter is crucial to understanding how the solar system formed, because it's crucial to understanding how did Jupiter formed. If Jupiter formed far from the sun, where it's cold, out of blocks of ice, frozen water at that great distance, you'll get a different amount of water inside Jupiter than if it formed closer to the sun where it is now, or if it formed some other way than from starting with blocks of ice. So just by measuring that one number, the amount of water inside Jupiter, we can learn a lot about how Jupiter formed, and that teaches us not just about Jupiter, but about the whole solar system, about how solar systems form, because Jupiter formed sort of out of the leftovers from the sun, and the rest of the planets formed out of the leftovers from Jupiter. All right, so how are we going to do that? We're going to measure that with the microwave radiometer. And I'll show you in just a moment what the microwave radiometer looks like. But it's a radio receiver that uses the natural radio emission from Jupiter to look at 6 different channels that can see inside Jupiter and get the water. So if we go to that little animation, you can see the antennas on the spacecraft. And the largest microwave antenna for that radiometer is so big it fills up a whole side of the spacecraft. And the other 5 take up another side of the spacecraft. In fact, the overall dimensions of our spacecraft were partly determined by making it big enough to hold those antennas. They're really important to us because they're going to get this key number. And the way we're going to do that is the fact that each of those channels can see a different depth into Jupiter. So if you go to that next slide, just to show each different channel sees below the water cloud or up to the water cloud, sees deep into Jupiter's atmosphere. And how deep they can see depends on how much water is in the atmosphere. What they see depends on the temperature of Jupiter's atmosphere as you go down, as it gets warmer, and that also depends on how much water is in Jupiter's atmosphere. So we can take the measurements from the microwave radiometer and use that to figure out how much water does Jupiter hold, which tells us about how did Jupiter form. If you go to the last picture I had, you can see that we also, because as the spacecraft comes by and it's rotating, because we can see each point on the planet from a range of different angles, we can do something like a CAT scan and get a 3-dimensional picture of Jupiter's atmosphere. So we're seeing each of the 6 channels at different depths, and we're seeing with each of the 6 channels at a whole range of angles. The result is we get a 3-dimensional picture of Jupiter's atmosphere to measure not just the water, but to see these amazing features like the Great Red Spot, a storm bigger than the whole Earth, or those belts and zones, jet streams moving at hundreds of miles an hour. We get to see those in 3D with the radio receiver instead of just that 2-dimensional picture that you can see on the screen. All right, so to talk a little bit more about how we can see inside Jupiter and go to greater depths, I'm going to pass it off to Jack Connerny.
Thank you, Steve. If we're going to understand Jupiter's interior, we're going to have to look a lot deeper than we can look with the MWR. And so to do that, we have 2 techniques. We measure the planet's gravitational field, and we measure its magnetic field. The gravitational field we measure just by looking at the orbit of Juno as it passes over the surface. The magnetic field we measure with a pair of instruments out at the pointy end of the solar array. And these two methods will probe the deep interior of the planet. And oddly enough, Jupiter's interior is quite a mystery to us. And that's ironic because it's made up of the 2 simplest and most abundant elements in the universe. That's hydrogen and helium. But the problem is it's under such great pressure in that environment that it behaves in very mysterious ways. So I can only explain to you what we think the interior of Jupiter looks like at this time. If we could roll the animation. So beneath the visible cloud tops that we see, there's a layer of molecular hydrogen that extends to great depths. And then beneath that, there's a core of metallic conducting molecular hydrogen. What happens is the hydrogen atoms are pressed shoulder to shoulder so closely together that the electrons that are normally bound to the molecular hydrogen are free to roam about the entire interior. That makes it a good electrical conductor. And then beneath that layer, we think there may be a dense core of heavy elements, everything heavier than hydrogen and helium. We don't know that that core is there. It may be 10 Earth masses, it may be 20 Earth masses, and part of this mission is designed to determine if there is a core at the center of Jupiter, and if that core was possibly the seed onto which the atmosphere collected and made Jupiter the largest planet in our solar system. So if I could have the next shot. This is a cross-section, a wedge shape of what we think the interior looks like. And you see that onion skin on top, that's the visible surface of the atmosphere that we're familiar with. And if you take a little chunk out of the topmost piece, that gives you the wedge to the right. And that's the region at top that the MWR can probe. That's the convective region of the atmosphere. It goes down to about 1,000 bars. With the magnetic field, we can penetrate deep below that surface. This cutaway illustrates the metallic hydrogen, the blue region, which is a good electrical conductor. And that region around Jupiter that Scott Bolton just talked about that is defined by Jupiter's magnetic field, that's generated by a dynamo that may be at the top of that metallic hydrogen region. We don't know for sure. It may be in the molecular hydrogen region above, but it generates a magnetic field that's 20,000 times more powerful than the Earth's magnetic field. And that is what gives Jupiter control over its own domain. So in order to determine where the dynamo is generated, we have to make a series of very accurate observations totally enveloping the planet. And so to do that, we've designed a mission plan that takes Jupiter in its science orbits very close to the surface, takes Juno, sorry, very close to the surface of Jupiter in its 14-day orbits. And if I could show that orbit clip, this shows you Juno in its elliptical orbit, racing over the surface of Jupiter at its closest approach, and at the end of its 14-day orbit, the furthermost extreme, it's about 45 planet radii away. Jupiter rotates every 10 hours, roughly. And so we phase these orbits specifically so that we come by the surface, we probe different longitudes, and we space them out very carefully so that by the time we're done, we've enveloped Jupiter in a dense net of observations that we need to characterize the magnetic field with the kind of resolution that we are searching for here. So if I can have the next animation, I'll show you how that works. After a few orbits to set up this mapping plan, the subsequent orbits come down separated by about 90 degrees, and you see Juno traveling from north to south, from pole to pole, with every orbit. We do a slight orbital trim maneuver, and we phase these so that subsequent orbits, periapsis passes, come in between previous periapsis passes. So by the time we're done with the nominal mission over 37 orbits, we have periapsis passes separated in longitude by about 12 degrees. And that gives us a complete map, completely encircling the planet, and these very accurate measurements we need to probe really for the first time how a magnetic field is generated by a dynamo and what it looks like at the dynamo surface. So that's probably the most exciting part of the mission for me. We can do this at Jupiter much more accurately and with much more resolution than we could ever do it in orbit about the Earth. And that's because Jupiter's dynamo is generated at a larger radius relative to the surface of the planet, so we have better signal to work with. And it's also because on Earth, when we try to image the dynamo, we have to look through a magnetized crust right beneath our feet. So Jupiter doesn't have that magnetized crust, and so there's nothing to obscure our view of dynamo action right down in the interior of the planet where it's generated. So that's a very, very exciting opportunity that we have in exploration of Jupiter that we could never do in orbit about the Earth. But this mission plan and this trajectory that's designed to go from north to south brings us, for the first time, above the poles of Jupiter into an entirely unexplored region of Jupiter's magnetosphere, where I'm sure very many discoveries await us. And so to talk about those discoveries, I'm going to hand it off to my good friend and colleague, Fran Bagenel, talk about the aurora.
Thank you very much, Jack. So as Scott said, the sphere of influence of this very strong magnetic field is vast. It's enormous. And it's sitting in this wind of protons and electrons that are streaming out from the sun at 1,000,000 miles an hour. And furthermore, as Juno has been observing, we know that that wind is gusty. It's blowing. And so this magnetosphere is changing and moving around as the gust of the solar wind comes and goes. So we have a very special opportunity with Juno coming in, observing the variable solar wind. And what we want to know is what influence that has on the magnetic field and the environment close to Jupiter. And the easiest way to do that is to look at the aurora at the same time as Juno is measuring the solar wind. So let me talk a bit about the Jovian aurora. If we could have the picture here. This is a Hubble Space Telescope picture looking in the UV, the ultraviolet light, at these blue, they look blue, but it's ultraviolet in fact. These are energetic particles come in and bombard the atmosphere of Jupiter and make it glow. And you can see three main regions here. You can see a main auroral oval, which is a sort of round region that's very bright and fairly steady. Unlike the Earth's, it doesn't vary very much. The aurora, that part of the aurora doesn't vary very much. We also see some bright spots, Io spot, the Europa spot, and the Ganymede footprint. These are the footprints of the magnetic field that go from the moons that are moving in this magnetic field. There are very strong electrical currents, 1,000,000 amp electrical currents, that are coupling these moons moving through the magnetic field to the planet. And where the charged particles that are carrying those currents hit the atmosphere, they make it glow. And so you see these spots associated with the moons, Io, Europa, and Ganymede. The third component of the aurora is the polar aurora, and you'll see bright spots in the center that are varying. Now, to illustrate all this and to help us understand the aurora, I'm going to show you an animation in a minute that was taken by Hubble in the past month or so. So the Hubble PI of this big campaign, Hubble's been looking at the aurora in the past few months, is here in the room, Johnny Nichols from the University of Leicester. And they've had about 25 days of observing many orbits of Hubble looking at the aurora. So let's have this movie of the aurora that was taken in the past month or so, and you can see, we're going to repeat it 3 times. This is a clip that is sped up about 300 times. It lasts about 45 minutes. And you can see the main auroral oval. You can see the spot of Io over on the right, and you can see a spot of Ganymede there too. But in the middle is this very variable auroral polar region where it's coming and going, and what we really don't know is what is controlling that variability. Is it the solar wind varying, or is it the interior of the magnetosphere, very dynamic magnetosphere, which swirls around and changes over time, fueled by material, in fact, from that volcanic moon Io? Or is it an internal effect, or is it external? So one way to find out is to observe the aurora with Hubble, and in fact there are many observatories here at Earth, either in orbit around the Earth or from the ground, looking at the aurora, looking at Jupiter at the same time that Juno will be going into orbit. And so we'll get a measure of the variability of the solar wind upstream, the variability of the magnetosphere as we observe it in situ with Juno, as well as looking at the variability of the emissions from Earth. So let's have a look at the next picture here. This shows you the size of what we're talking about. So if you look at the Earth, the size of the aurora there, shown in green emission, the Earth's atmosphere glowing, is about the size of the United States, the sort of size of the main auroral region on the Earth. But when we compare it with the size of Jupiter, of course Jupiter is about 11 times the size of the Earth. The auroral region is about 5 Earths across. So this is a big region, and it is emitting a lot of power, about 100 times the aurora that comes from auroral power that comes from Earth. And it'll be telling us about the magnetosphere. And in particular, if we have the last of my pictures, you'll see here, we have this unique situation with Juno. Flying over the poles, we look down on the aurora in the UV and the infrared and in the visible with JunoCam. And then we will be able to also fly through the region where the charged particles are coming in and bombarding the atmosphere. And so we'll be able to measure the acceleration processes that cause these auroral effects, these emissions. And at the same time, we'll be measuring plasma waves and the perturbations in the magnetic field associated with those currents, and the radio waves that we've known for many decades that come associated with the auroral emissions. So this is a very unique opportunity to be looking at this very interesting phenomena, very bizarre glowing and flickering and so on associated with the aurora. But we've never been able to get up close and really observe these processes. So we can then compare them with what we see at Earth, what we see at Saturn. Are the physical processes just similar, but we have a stronger field at Jupiter? Or do we have to really go back to the fundamental physics and work out what's really going on here? So we're really looking forward to a very exciting opportunity to look at the aurora in many different ways and different aspects. So I'll hand this back to Scott.
Thanks, Fran. So you can tell we're all really excited. The whole team is so thrilled. We're really getting there, and we're so close to Jupiter. We have a big event on July 4th, as you know, to go into orbit. It's really important to us, and we're about to jump on that Jupiter train. So we also have a camera that's called JunoCam, and it's a public outreach camera, and we make those images and even the data available to the public through our websites. And I want to show you another picture that we're releasing today from JunoCam. Can I get that picture? So this picture was taken a couple days ago of Jupiter. Some of the unique or exciting ideas is that not only can you start to see the colors and the zones and belts of Jupiter, but you can actually see the red spot in this image. And you see 3 of the Galilean moons. The lower one is Europa. It's actually the second moon. The one just above that is Io, and that's the closest Galilean moon. That's the most volcanic body in the solar system. And then the furthest out one is Ganymede, and those bodies those are the satellites moving around Jupiter. Those are 3 of the 4 Galilean satellites. And in the auroral pictures that you saw that Fran just showed, the footprints of those are in the aurora. So there's an umbilical cord through the magnetic field that's tying those moons into Jupiter. And they're sending particles back and forth. And when the particles from those moons go into Jupiter, they light up. And that's kind of cool. So I hope you all join us. We're getting really close. We're really excited. We want to invite everybody along for the ride. Come see us on July 4th. Thank you. Back to you, DC.
Thank you, Scott. So we're going to open it up to the floor here at JPL for any questions from the media. If you have a question, just raise your hand. Emily over there, and please wait for the microphone. Please state your name and media affiliation.
Hi, Emily Lakdawala, the Planetary Society. I think this is for Steve. It's a question about the hydrogen that you're looking for in Jupiter. How do you know that the water that you're going to be measuring there is primordial water, that is not kind of exchanged with the supply of molecular hydrogen in Jupiter? How do you tell the difference between those two?
Okay, so remember, it's really the oxygen that we're after, right? Water is H2O. Jupiter is mostly hydrogen. The next most abundant element is helium, but the third most abundant element in the solar system is oxygen. And yet, so far, we haven't found very much oxygen in Jupiter. So we're looking for water because that's the form in which oxygen will be found. But it's the oxygen we're after. And it's got to be primordial because you can't really affect Jupiter with small things. If, a few years back when a comet hit Jupiter, the mass of that compared to the size of Jupiter is very small. So the amount of water we find in Jupiter should be representative of the water that got there when the planet formed in its early history. Does that answer what you were asking about? Thanks.
Great. Thank you. The gentleman in the back row there, please state your name and media affiliation.
Hi, I'm Devin Coldaway with TechCrunch. I was curious, Steve, you mentioned the magnetic field being about 20,000 times stronger than the Earth's. I'm curious about the scales of other major deviations, like the scale of the pressure that would be needed to create metallic hydrogen, radiation and stuff like that. I'm just curious about the other sort of huge magnitude factors in Jupiter and whether we're going to find out much more about those.
So it's actually Jack who mentioned the magnetic
Excuse
field,
me.
and he's our magnetic field expert as well. So I'm going to let him answer.
Okay, thanks, Steve. So the dynamo generates this magnetic field. It needs a lot of energy, a lot of power to do it. But you have to have a conductive fluid, and it has to be in some kind of a convective motion that drags the magnetic field around with the fluid and manages to sustain a dynamo, just like the Earth's dynamo. Of course, the Earth's magnetic field flips every couple 100,000 years. We don't know if Jupiter's magnetic field flips or not. I suspect it does. But it's enormously strong because everything about Jupiter is enormous. The gravity is huge. The planet itself is huge. The part of the planet that is conductive, that can participate in a dynamo, is huge. So it's no surprise that it generates a magnetic field that's about 20,000 times more powerful than the Earth's magnetic field. But Jupiter itself is such a large body that when you're at the surface, you're kind of far from where the field is generated. And at the surface, the field magnitude is only about 20 times the field magnitude of the surface of the Earth. But even still, this spacecraft is going to fly in space through a magnetic field that is 10 times greater than anything we've ever experienced. And so that's one of the curiosities. We're going to have to see how it performs when we do that.
Great. Gentleman in the front row.
Jay Pasikoff, representing the Huffington Post. You have staged the close flybys to cover all the longitudes of Jupiter, but Jupiter's surface, of course, is in differential rotation. How are you planning to uncouple the atmosphere, or are you just looking through the atmosphere and it's more stable below? And as a second question, can you give us some timeline for the insertion when the key times for us to be worried or pleased on July 4th will be?
So we'll let Jack take the first part of the question, and then maybe Ed can answer the second part.
Okay, so we phase these orbits so that we get the equally spaced longitudes. What's happening at the very top of the atmosphere, the parts that we see, the belts and zones that are red and white, they are in differential rotation. You're very right. That's not where the magnetic field is generated, though. The magnetic field is deep below that. And it's a good question. We don't know how deep that convective motion is in the atmosphere. But what we do know is that magnetic field rotates like a clock. We've been measuring via the radio emissions we get from Jupiter for 40, 50 years, ever since it was first discovered.
65 years.
Okay, Frank. 55. You get the idea.
When I was born, I know.
We've been measuring it for a long, long time. And so it's very precise. It's like a clock. And so we know that the interior rotates as a body with that 10-hour rotation rate. Thank you, Fran.
I want to add in here that we measure our longitude, what we call system 3 longitude, is based on the magnetic field. So we use that as our way of measuring longitude and mapping it around. We don't care what happens to the clouds. The clouds come and go. What we're interested in is that magnetic longitude.
So you can see it's not necessarily easy to manage this team. So there are atmospheric scientists that are interested in the field, and we in the atmospheric clouds too. So we have them on the team. But Fran's right. So the rotation of Jupiter, the rotation period itself is basically defined by the rotation of the magnetic field. And then, but one thing you should realize is we also measure the gravity field very precisely during this mission. And one of the goals of that is to understand how it's rotating inside. How deep, and when does that rotation start, and how does it work? Let me go back to Ed for the details of the orbit insertion times.
Yeah, the two key times that I would keep an eye on are when the main engine burn starts and when it stops. And the signal that we get, the event will be over by the time we see that happen. There's 48 minutes of light time for the signal to reach from Jupiter to the Earth. We get the signal that the main engine burn started at 8:18 p.m. Pacific time, and then 35 minutes after that, at 8:53 p.m., we'll see the signal that the main engine burn has stopped. There's obviously activity before and after that, and we can get you a more detailed timeline. But those are the really two key times on July 4th.
Okay, thank you, Ed and panel. And I understand we have a question from media on the phone. So please state your name and media affiliation.
Hi, thanks, DC. It's Irene Klotz with Reuters. I have a couple questions. For Scott, you mentioned in your opening comments that you still feel a little nervous about the upcoming burn and orbit insertion. If you could maybe just talk a little bit about what about that gives you pause, and also give us the speed that Juno will be moving relative to Earth just before the burn starts, and the speed of the spacecraft when the burn is finished.
Okay, so did I say little in the nervous? That was probably a misstatement. So yeah, I'm nervous. I have mixed emotions. I'm excited and with anticipation, of course, because we're finally arriving. But I've also have tension and nervousness because there's a lot riding on what happens July 4th. We have to perform this critical maneuver. As Ed described, the rocket motor has to burn at just the right time, in the right direction, at the right moment for the right amount of time for us to get into orbit. And if that doesn't all go just right, we fly past Jupiter. And of course, that's not desirable. We would like to go into orbit to do the science. So that part of it is challenging. And of course, the idea that we're going into this planet, this extreme environment that is so much greater than anything we've ever experienced before, is all happening for the first time when we have to fire this complicated, delicate maneuver. And having the lack of any control, it's all automated, right? So the light time between Jupiter and Earth is 40 minutes or so, or more than 40 minutes. And so the whole burn is about 35 minutes. So everything's automated. The spacecraft's a smart robot. We've tested everything. But still, everything's riding on it. And I kind of felt the same way when I was at the launch. I was so excited to be there that we were finally leaving Earth and launching on the rocket to go to Jupiter. But I kept looking and thinking, gosh, the whole spacecraft's on top of that rocket. What if something happens? And that's a big risk, you know. And of course, you don't get the great gains of reaching out, you know, and exploring and learning about nature unless you take those risks. So I'm not against the risks, but it doesn't mean that I'm not nervous. The second part of the question was the speed. So I may not remember all of these. We may have to get that to you. But I think at the time that we arrived there, right before the burn, we're moving about 160,000 or 165,000 miles an hour. So we're relative to Earth. So that's incredibly fast. And I don't think we've had any human object that's moved that fast that's left the Earth. After the burn, somebody would, I don't have that number at the top of my fingertips relative to Earth.
Right, we'll get that.
Thanks. The other question I had is just about the kind of the big picture science of understanding more about how and where Jupiter formed. What is the kind of the range of opinions on where the planet started off and how it got to where it is today? I know that's a really big question for a short press conference, but if there's a way to kind of generalize even just how divided the community is on the question, that'd be helpful. Thanks.
Well, I think there's There's a lot of scientists on the team, and there are many scientists not on the team, and there's not a consensus on the answer of where Jupiter formed. You know, initially it's at 5 times the distance of the sun, and that was sort of the idea traditionally. Now there are models that show planetary migration might exist. Jupiter may have moved to its present location from further out, forming further out. Trying to explain the composition. Some models show Jupiter forming out near Uranus or Neptune and then moving in. But the truth is we don't know the answer to that, and one of the big clues will be the oxygen abundance and how much water is in Jupiter. That will help us, but also the core will also help that.
Great. Thank you, Scott. I understand we have some questions from social media. Jason?
Indeed. First question here comes from RIA Novostovi reporter from a newswire service here asking, how will NASA deal with solar panel fouling and degradation in the course of the mission? What are the chances that it will last longer than planned?
I can take it. So we have solar arrays that are tested and specifically designed to be able to last through the cold temperatures and the high levels of radiation. They have a cover glass on them. But we also have designed into the mission the ability to have some of those decrease in their efficiency for producing electricity. And so if there's a huge amount of energy that's lost, more than we've accounted for and more than the margin and the reserves that we've already taken into account, we can reduce the amount of energy consumption by time sharing on the scientific instruments, but we don't think we're going to need to do that.
All right. Next question comes from a Twitter user, Perlobby, who asks, what's the average lifespan for the instruments given Jupiter's environment?
So I'll take that one too. That varies a little bit. There are the instruments that have all of their electronics inside the vault are designed to last through the end of the mission, all the way through the completion of all the orbits. We have a couple of instruments that were added late that we did not feel we needed to put into that radiation, the same kind of level of radiation protection. I think the infrared camera and the visible camera are outside that box, and they were designed to be able to last long enough to accomplish all the science objectives. But our analysis now indicates that they'll probably last much longer. So, but there's a little bit of variation. So some of them last through about the first half of the mission, but the bulk of the science instruments go all through the whole mission.
All right, coming off of our Ustream feed here, Penn State Phil asks, if Juno determines there is a solid core, can it detect what elements that core might be made of?
I'll let Jack take that.
Well, thank you, Scott. I don't believe so. We'll know what the mass is, the summation of mass there, but we won't be able to identify whether it's iron or lithium or what the elements are.
It might also be pointing out, because the questioner assumed it was solid core. We're talking about a dense core in the center of Jupiter. It may not be a solid.
So I've been going to all these science team meetings for many years, certainly since launch, 5 years, and every time I have a science team meeting, the interiors group come up with a different theory for how this material works at these very high pressures. We're working in a new environment, which we don't know the physics of how things work at these high pressures, and they're coming up with theoretical quantum mechanical models, but they can be wrong. And so we're going to make the observations that will be key, they will be important. But I'll bet you that the theorists are going to keep adjusting and adapting their models, but we will have constraints.
Wonderful. This last question comes from Twitter user Carl, who asks, when will we get the first images from Jupiter after JOI?
When?
Turn the instruments back on about 2 days after. So.
Yeah, we turn the instruments on just a couple of days later, but I'm not sure what the schedule is to send down the first image after that happens. we'll have to get back to you on that.
Okay, great. I understand we have a follow-up question from Irene Klotz at Reuters. Irene, go ahead.
Hi, thank you. For Scott, I just was wondering if there is something more dynamic or more challenging about going into a polar orbit around Jupiter versus the orbit that Galileo put itself into many years ago. And also, if you could just characterize, you've portrayed this mission as the spacecraft that will come closest to Jupiter, but just was wondering if you could put that into context with the hour of data that the Galileo atmospheric probe was able to send back. Thanks.
Yeah, well, the Galileo probe, of course, went into Jupiter, but when we talk about the closest, the spacecraft, we mean in orbit. So Galileo probe wasn't in orbit around Jupiter. This is the closest orbit that the spacecraft has gone into around Jupiter, and it's considerably closer than Galileo's orbit, which was started out at about 4 Jovian radii, and then went out further from that until the very end of the mission. They of course went in to Jupiter, but again, they weren't really in orbit. They were going in to dispose of the spacecraft. The polar orbit itself is challenging, but when you're coming in from essentially infinity and you're arriving at Jupiter, you can target over the pole or over the equator and basically enable yourself to choose that inclination. So the challenging part of or aspect of the Juno orbit is the fact that we're so close. We're both polar and we're going in so close that we're threading a needle between the radiation belts and the atmosphere and getting into what we believe is a gap in the radiation. And each time you go over the poles, there's parts of the radiation belts that are reaching out into higher latitudes, and you're getting closer and closer to those. And so that polar part of that polar aspect of the magnetosphere puts you in jeopardy because you're closer to these other parts of the radiation belts.
Great. Thank you, Scott. I understand we have a follow-up from Emily.
Yeah, you showed data from the Plasma Waves instrument and JunoCam. I'm wondering about the rest of the science instruments. Have they been on? Have they taken data yet that's relevant to the study of Jupiter? Have they all gotten data? Are the scientists happy?
I think the scientists are generally happy. We've got a lot of data. Not all of it is easy to analyze and interpret, so we've provided some insights into some of the data that were more straightforward to understand. But we are definitely analyzing the other data that we get throughout about the solar wind and UV data on the aurora and things that we are taking ourselves. And as we get through that and interpret it and get ready to write the publications and understand it, we'll of course release it.
Great. Well, thank you. I think that's going to do it for us here today at JPL. This is the first of 2 briefings, though, so please stick around for the second one, which will start pretty close to the top of the hour. For more information about Juno, please visit nasa.gov/Juno and missionjuno.swiri.edu. And for those of you who want to join in on the conversation, visit on Facebook or Twitter, facebook.com/NASA-Juno and twitter.com/NASA-Juno. Thank you for joining us today, and please join us as well on July 4th. It's a big day for us here at JPL and for the Juno mission. Things start off at 9 a.m. Pacific Daylight Time with another briefing here in Von Karman Auditorium, and then at 7:30 p.m. Pacific Time, we'll start commentary for the Jupiter orbit insertion. So want to thank you for your time, thanks the panel for their time, and have a good day.